Locating an object in a void requires a mathematical reference frame. Without an explicit coordinate system, spatial orientation cannot be defined or communicated. In a three-dimensional Cartesian space, every calculation begins at the origin. This absolute center is the 0 point for all three axes. We can represent a physical object as a discrete point, labeled P, defined by specific x, y, and z coordinates. Drawing a line from the origin to this point creates the position vector, denoted as vector r. Algebraically, this vector is the sum of its components, xi hat, yj hat, and zk hat. This single mathematical structure defines two distinct properties of the object's location. The first is magnitude, the scalar length representing the total Euclidean distance from the origin to the point. The second is direction, the specific trajectory the vector follows through the three-dimensional grid. Complex systems often require these properties to be handled separately. For example, a navigation system may need to change a vehicle's heading without altering its speed or distance traveled. To achieve this, engineers must isolate the pure direction of the vector, removing the influence of its total length through a specific geometric process. The isolation begins by calculating the vector's total magnitude. We find this Euclidean norm by taking the square root of the sum of the squared coordinates. We then measure the orientation by identifying the angles formed between the vector and each principal axis, labeled alpha, beta, and gamma. The cosines of these three angles are known as the direction cosines, L, M, and N. Each cosine is a ratio, the coordinate of a specific axis, divided by the vector's total magnitude. Squaring these three cosines and adding them together always results in a sum of exactly 1. This identity allows us to define a unit vector, a version of the original vector scaled down to a magnitude of exactly 1. In this state, the values of L, M, and N serve as the scalar components of the unit vector itself. Because the magnitude is fixed at 1, these components represent orientation stripped of scale. While the original coordinates show where the point is, these normalized values show only which way the vector is pointing. Because the sum of the squares is always unity, direction cosines provide a consistent method for calculating trajectory regardless of the distances involved. This geometry is the standard for controlling systems in physical environments. For instance, in aerospace engineering, maintaining a satellite's attitude requires constant, precise adjustments relative to an inertial reference frame. The unit vector extending from the satellite's center of mass defines its current orientation in space. Flight computers manipulate the L, M, and N variables to execute pitch, roll, and yaw adjustments, translating the math into physical thrust vectoring. This same logic governs the behavior of electromagnetic energy. The pointing vector dictates the directional flow of energy from an antenna. RF engineers use direction cosines to calculate spatial polarization angles, ensuring the signal is oriented correctly for the receiving hardware. Modern beamforming depends on this precision. If the direction cosines of a 5G signal are slightly off, the energy entirely misses its target. One application moves high-velocity hardware through a vacuum. The other moves invisible data through the air. In both cases, direction cosines are the primary mechanism for steering through the physical world. This geometric framework remains valid even when the space we are navigating is entirely digital. In computational science, we treat data structures as n-dimensional vectors. A word is represented by an array of hundreds of numerical values. These values are coordinates in high-dimensional space, turning a word into a vector with a specific trajectory. To compare these concepts, AI models use an algorithm called cosine similarity. The algorithm divides the dot product of two vectors by the product of their magnitudes. This calculation is identical to finding the direction cosines of the angle between them. By isolating the direction cosines of these data vectors, the AI can measure their semantic closeness. Two words are related if their vectors point in nearly the same direction. The math does not change as we scale. The same normalization used for a three-axis grid applies to a model with 10,000 dimensions. This demonstrates a universal property of vectors. The geometry used to steer a satellite is the same geometry AI uses to understand human language. Applying these concepts requires translating the geometry into a programmable format. We store spatial coordinates in software using a 1D NumPy array. This array represents the vector's position in the coordinate system. The code uses the linalga.norm function to calculate the Euclidean distance, providing the magnitude we need for normalization. Dividing the coordinate array by this magnitude algorithmically strips away the scale. The output is a unit vector, where each component is a direction cosine. The simulation reflects this by snapping to a length of exactly 1. Changing the initial inputs in the array causes the unit vector to reorient instantly, demonstrating how the code controls trajectory. This complex spatial extraction is executed in only 3 lines of Python. Programming provides the operational interface for vector algebra, converting these geometric ratios into instructions the system can execute. We have traced the path from the origin of a 3D grid to the high-dimensional clusters used by modern AI. Throughout this transition, the direction cosine remains the fundamental tool for isolating orientation from magnitude. Aerospace dynamics, radio frequency engineering, and machine learning all rely on this single mathematical property to navigate their respective environments. These textbook principles provide the specific coordinates and orientation logic required to build and maintain modern technology. Mastering vector algebra is the baseline requirement for any engineer seeking to architect the complex systems of the future.